Welcome to this lesson on activation energy, one of the most fundamental concepts in chemical kinetics. Activation energy represents the energy barrier that must be overcome for a chemical reaction to occur. Think of it as the gatekeeper of chemical reactions. Understanding this concept will help you predict reaction rates and explain why some reactions happen instantly, while others require external energy input like heat or catalysts. Activation energy, denoted by the symbol E sub A, is defined as the minimum energy required for reactant molecules to overcome the energy barrier and successfully form products. It is measured in kilojoules per mole or joules per mole. Every chemical reaction has a specific activation energy value. Without this minimum energy, molecules simply bounce off each other without reacting, even if they collide. Only when molecules possess energy equal to or greater than the activation energy can bonds break and new bonds form to create products. To understand activation energy better, imagine climbing a hill. When you climb, you need to exert energy to reach the top before you can easily descend down the other side. Similarly, in a chemical reaction, molecules need energy to reach what we call the transition state, which is like the top of the hill, before they can transform into products. Just as a steeper hill requires more effort to climb, a higher activation energy means molecules need more energy to react. This analogy helps visualize why energy is needed even for reactions that ultimately release energy. An energy diagram is a powerful tool for visualizing activation energy. The horizontal axis represents the progress of the reaction from reactants to products, while the vertical axis shows the energy level. The curve shows the energy path molecules take during the reaction. Notice how the energy rises from the reactant level to reach a peak at the transition state, then falls to the product level. The activation energy, E sub A, is the difference in energy between the reactants and the highest point, the transition state. This diagram clearly shows that molecules must gain energy before they can proceed to form products. Several factors determine the activation energy of a reaction. First, bond strength plays a crucial role. Stronger bonds between atoms require more energy to break, which increases the activation energy. Second, molecular orientation matters because molecules must collide in the correct alignment for bonds to break and form properly. Third, reaction complexity affects activation energy. Multi-step reactions often have higher energy barriers because multiple bond-breaking and bond-forming events must occur. Finally, catalysts are special substances that lower activation energy by providing an alternative reaction pathway with a lower energy barrier, making reactions proceed faster without being consumed themselves. The Arrhenius equation, mathematically, relates activation energy to the rate constant of a reaction. The equation is K equals a times e to the power of negative E sub A divided by RT here. K is the rate constant, A is the frequency factor representing the number of collisions with proper orientation. E sub A is the activation energy, R is the universal gas constant with a value of 8.314 joules per mole Kelvin. T is the absolute temperature in Kelvin, and E is Euler's number, approximately 2.718. This equation shows that as activation energy increases, the rate constant decreases exponentially, meaning the reaction becomes slower. Conversely, increasing temperature increases the rate constant, speeding up the reaction. The magnitude of activation energy dramatically affects reaction rates. Reactions with high activation energy are inherently slow because only a small fraction of molecules possess sufficient energy to overcome the large energy barrier. These reactions typically require significant heat input or a catalyst to proceed at a reasonable rate. Examples include the combustion of wood, which needs an initial spark or flame. In contrast, reactions with low activation energy are fast because many molecules naturally have enough energy to surpass the small barrier. These reactions can proceed readily at room temperature. Examples include acid-base neutralization reactions and many precipitation reactions that occur instantly when solutions are mixed. let us summarize the essential points about activation energy. First, activation energy is the minimum energy barrier that molecules must overcome to react and form products. Second, the relationship between activation energy and reaction rate is inverse. Higher E sub A results in slower reactions, while lower E sub A leads to faster reactions. Third, catalysts are valuable because they accelerate reactions by lowering the activation energy, providing an alternative pathway without being consumed in the process. Finally, temperature plays a vital role because it affects the number of molecules that possess energy equal to or greater than the activation energy needed to react. Understanding activation energy is crucial for controlling and optimizing chemical reactions in both laboratory and industrial settings.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.